Hello. Our is Group 9, and we will introduce our project. Our project name is Wireless Monitoring and Control of Drones, and our group member consists of 5 people. Okay, then first I will introduce the hardware of our project. First, our flight control board is Pixhawk, which has several key features, such that the 168 megahertz or up to 252 megahertz for the Cortex M4. And it has 14 PWM and server outputs, and abundant connectivity options for additional peripherals such as the UART, IC, and also the CAN interface. And it has a micro SD card for high rate logging over the extended periods of time. And this board is our radio transceiver. We use the Atmega 256 RF-R2 X-Plan Pro board. This board is provided by the teacher, and we choose it because it has several features, such that it supports by hardware-assisted multi-pan address filtering, and advanced hardware-assisted reduced power consumption, and it embedded a high-performance, low-power AVR 8-bit microcontroller, and it also has hardware security. The AES is a true random generator. And then it is the architecture of our hardware. Our hardware included several components. One flight control board, which is Pixhawk, and 3 X-Plan Pro board for the radio transceiver, and also a PC to communicate with XPB1 by the UART. The XPB2 and FPB are installed on a quadcopter or a UAV. They communicate with each other through the UART interface. And there are 2.4 gigahertz RF transceiver and antenna on FPB, so they can transfer wireless data with each other using half duplex communication. XPB1 also communicates with a PC by UART interface. Okay, and XPB3 is act as another quadcopter to simulate the interference in the reality. So at the same time, there are 2 XPB to communicate with the XPB1. And then I will briefly introduce our software. Our software is divided into 3 parts. The part 1 is the flight control system, which is installed in the flight control board. And the second part is radio transceiver system, which will drive the radio transceiver and make it work to communicate. And the last one is the ground station, which is run in the PC. And actually we use an open source ground station software. And the name of the ground station software is the QGround controller. Yeah. And this picture is system architecture for the flight control board. We design it, and we divide it into 1, 2, 3, 4, 5 layers. And the bottom layer names the driver layer. It included several drivers for the peripheral components, such as the GPIO, ISC, SPI, USART, and timer, and so on. And after the driver layer is the kernel layer. We embedded a real-time system in our flight control system, and we use the RT thread as our RTOS. And it has several modules, such as the service module and the scheduler, which is provided the function for schedule the tasks, and also the mem manager and the thread and the file system, and so on. And the next layer is the hardware abstract layer, which is a layer that supplies some abstract API for the up layer, and and it have the sensor and also the bus interface. The sensor will supply the function to get the data or configure the sensor. And next layer is the framework. Framework include the sensor manager, which will take the responsibility to manage the sensor behavior, and also the Mavlink. Mavlink is a protocol for the UAV. And the up layer is the application layer. In our project now, there are just 2 threads. Thread 1 is take the charge of communicating with the sensor, and thread 2 take the responsibility to communicate with the radio transceiver. And this picture is describe the process of the passage. First, in our flight control system, we will create a Mavlink message, which will include several information, such as the sensor data and also the attitude of the drones. Then the Mavlink message will be transferred to the radio transceiver, and this is the MAC protocol layer data unit. Also saying it as MPDU in MAC layer. Then the MPDU will be transferred to physical layer and be packed to physical protocol layer data unit. Also name it the PPDU. Okay.
In this part, we will discuss about why we choose CSMAC protocol. We consider wireless sensor networks which share the same wireless communication channel. MAC protocols specify how nodes share the channel and are classified into either contention-based or contention-free protocols. We'll compare the two mechanisms in the next, but before that, we show the balance of requirements in WSN, which is different from traditional wireless networks. First and foremost is the need to conserve energy. We should avoid energy problems such as collision, overhearing, protocol overhead, and idle listening as much as possible. Secondly, a design constraint somewhat related to energy concerns is the requirement for low complexity operation. Sensor nodes shall be simple on the chip and cannot offer plentiful resources in terms of processing power, memory, or energy. Therefore, computationally expensive operations like complex scheduling algorithms should be avoided. Further important requirements for MAC protocols are scalability and robustness against frequent topology changes. As cost, for example, by nodes powering down temporarily to replenish their batteries, by energy scavenging, mobility, deployment of new nodes, or death of existing nodes. The need for scalability is evident when considering very dense sensor networks with dozens or hundreds of nodes in mutual range. Now we compare the two kinds of mechanisms. Contention-free protocols. The available resources are divided between the nodes such that each node can use its resources exclusively, without the risk of collisions. Contention-based protocols. Nodes may initiate transmission at the same time. We did not adopt contention-free protocols mainly because they lack of scalability. Namely, it is necessary to determine the number of nodes in advance, so that corresponding time slots can be allocated. However, the number of nodes in the space is uncertain. Besides, we noticed that very tight time synchronization, as needed for TDMA with small time slots, would require frequent resynchronization of neighboring nodes, which can consume significant energy. In contrast, the contention-based protocols have good scalability and low complexity. There is no need for joins to communicate with each other based on the mechanism, which means that joins only have to communicate with GSS. Obviously, contention-based protocols are more suitable for our unmanned aerial system. Hence, we decided to choose between CSMA and Aloha. Main difference between Aloha and CSMA is that Aloha protocol does not try to detect whether the channel is free before transmitting, but the CSMA protocol verifies that the channel is free before transmitting data. Thus, CSMA protocol avoids collisions before they happen, while Aloha protocol detects that a channel is busy only after a collision happens. Due to this, CSMA is more suitable for our networks, where multiple sources and destinations use the same channel. However, hidden terminal problem and exposed terminal problem still exist in CSMA protocol. Based on this, we finally decided to apply CSMAC, which can address hidden terminal problem and reduces collisions to our unmanned aerial system.
Project we use the unslotted CSMAC protocol. This is the workflow of CSMAC. First, by setting some parameters to the transceiver state control register, we can turn the transition mode on. At the same time, initialize the times of CSMA performance at 0. Then set the TRX state register at the busy state. After that, we can get a random number. Its value is
between 0 and 2 of the b power minus 1. be is the backoff exponent. It is related to how many backoff periods a device shall wait before attempting to access a channel. NB is the number of times of CSMA algorithm performed. So the random backoff time is equal to the product of the random number and the unit backoff period. By CCA, we can know whether the channel is idle or not. If the channel is busy, the system will go back to the upper workflow with a random period of time and try again until the channel is free or the transition failure. On the other hand, the frame control field consists of the ACK request. If no ACK request, the status of TRAC status register will be set as success. Because of the register bit slotted operation is 0, an acknowledgement frame is automatically sent if requested. When receiving an ACK and the ACK is also valid, the system will decide whether the data pending needs to be performed. The TRAC status register will be set different status. In the end, both success and success data pending means the data transition is successful.
Now let's talk about the data transmission. Firstly, look at the picture. From the picture, we can see that there are 5 states in the communication process except the reset. The state in the center, named TRX off, is the initial state. Below that, at the right, are TXARET on and busy TXARET, which are for sending data. At the left are RxACCK on and busy RxACCK, which are for receiving data. The initial state can be reached immediately after power on or reset, or using command force TRX off and TRX off to this state. Then let's talk about the procedure of send first. Once there are data need to be sent, we should use command TXARET on to the state TXARET on, and then data will be written into a frame buffer. After that, we use command TR start to change the state into busy TXARET. In this state, a frame transmit and an acknowledgement procedure will be done. After receiving successfully an acknowledgement frame or that the times of retrace and are bigger than the mask retrace, there will have an interrupt eventually, and we can know the transmission status by reading register. Then the state will change back to TXARET on automatically. Then send is over. And then let's switch to receive. Once there are no data need to be sent, we will set the state to RxACCK on for receiving data. We use the command RxACCK on to reach this state. In this state, the radio will listen to the channel, and after a start of frame is detected, the radio transceiver will change to state busy RxACCK on. In this state, a frame receive and an acknowledgement procedure will be done. Then there will have an interrupt to indicate the completion of the frame reception. The data received will be stored in a frame buffer, and the state will be back to RxACCK on. Then receive is over. And this is the part of how data transmit.
Hi, this is Ramakrishnan. what we have implemented in this project regarding the security mechanism consists of basically two parts. One is key management and authentication. The next phase consists of encryption. So there is a lot of communication going on between these two nodes, and we have some security mechanism to make sure that they are communicating securely. So the first thing is key management. Like, it consists of all the key sharing systems between the two nodes, where they are using the same keys are being generated every time, and whether the entropy is maintained. So all these things come under the key management, and also charity. And the next step in the same phase, it is authentication. It's like virtual authentication. Like, we have two nodes, flight control system, and the other one is the ground station. So some information is needed to prove their own authenticity to each other. So if the flight control system wants to prove its authenticity to the ground station, it sends some packets, it sends a challenge, and it gets a response. If the challenge and response are matched, so if there are no bad effect on the packets received, sent and received. So yes, so this is going to be a valid one. So each of them will be authenticated to one another. And the next phase is the encryption. So in encryption, it's the hardware has its own implementation. The processor has AES embedded in it. So it's a strong cipher. It's a great standard. It's one of the best solutions for encryption, that too for the packets on the fly. AES is one of the best solutions for it, and it also creates a secure channel between the two transceiver nodes. So implementing AES is kind of a huge security wall, and it is quite difficult for the attackers to penetrate through. So like attacks like man in the middle, replay and relay and all, they're quite difficult with AES encryption implemented between these nodes. So yeah, it consists of 4 rounds, like 4 steps. One is adding the round key. So the key for each and every round is always added. Like, there are 10 rounds in AES 128-bit. So for each round there's a separate key. So this is an additional security measure, and it has a substitution box. It's a pre-generated one, and in some way the plain text will get substituted, and it also has shift rows and mixed columns, where the byte columns and byte rows get scrambled upon. So it is still more safe and secure. So we've implemented these two mechanisms, these two phases, the key sharing, authentication, and the encryption. So with all these, we have implemented them right. So it's all in implementation always. So we have implemented them in such a way that it doesn't affect the efficiency of the system. And yeah, we have a very good system which is safe and secure from the attackers. Thank you.
Okay, let me show how our project works. Firstly, I will introduce each board in our project. This board is a flight control board. It's a Pixhawk. This board will connect all kinds of sensor data, and also will compute the attitude of the drone according to the sensor data. Then this board will send all this data continuously through the UART to this board. This board is XPB, namely X-Play Pro board. Okay, these two boards, the energy of these two boards is supplied by this PC. Then this board is connected to the PC by the UART, and this board, when this board receives the data, it will send all this data to the ground station. This is the interface of the ground station. Okay, and this board XBB3, it works as another quadcopter to simulate the situation that existing the interference. So all these two boards will continuously send the data to this board at the same time. Okay, then I will show how this works. Okay. Firstly, we can see this board is the attitude of the drone, and this board shows the direction of the drone. Okay. When I move the FCB, we can see the attitude will change accordingly. And when I turn around, the direction will change accordingly. And then I will show the sensor data. First, we can see the accelerometer data. The accelerometer data consists of three axials data, including x, y, and z. When I keep the FCB stable, we can see the accelerometer data are also stable. When I move the board, when I move the board, we can see the data will change accordingly. Okay, and then it's the gyrometer data. Also, when I change the board, the data will change accordingly. The last data is the magnetic data. When I move the board, the data will change accordingly. Okay, so this is how our project works. Thank you.